Section 1.3, Scientific Measurement. Now we're going to start looking at some material where we actually have some problems that we can do. And so scientific measurement is a good example of that. Much of what we will do in general chemistry is calculation based on what we call measurements. A measurement is an observation that you make. For example, you might observe that your room that you're in right now is a certain length. A measurement has a number associated with it, which is quantitative. So, for example, the length of your room might be 12 something. The other thing that we need, other than the number, is the unit of measure. So, for example, a room which is 12 inches is not the same as a room that is 12 feet or 12 yards. A 12-yard long room would be pretty long. A 12-foot room, 12 feet, would be maybe a normal-sized room, or on the small side perhaps. A room which is 12 inches, of course, would be tiny. So we need a number, and then we also need a unit. Now, one of the problems that you will find as you go through chemistry is that we have two different systems of units that we use. One is called the international system. The other one is called the imperial system or English system. And so, unfortunately, we use both of them. You'll find that we use more of the SI, the international system, than we do the imperial units, but they both do exist. So examples of the English system, the imperial system, are inches, feet, yards, miles, ounces, pounds. Examples of the SI system would include meters or centimeters or kilometers, grams or kilograms. Those are the SI units. So in the first picture here, the first figure, 1.9, there's a picture of four different typically used chemical glassware instruments. The one on the left, figure A, is called a volumetric flask. And we use that to measure volumes, the amount of space that something takes up, very, very accurately, typically to about 0.1% accuracy. The one on the second one from the left, the graduated cylinder, figure B, is also made to measure things accurately, but not as much so as the volumetric flask. So this is a 25 milliliter graduated cylinder. The one on the right of that is figure C, is called a pipette. And this one is also designed to measure volume very, very accurately. You'll see there's a little ring up on the neck of it, up toward the top. If you pull up a liquid into this pipette up to that ring, it will deliver 25 milliliters. And then the one on the right is called a burette, and same idea, it's used to measure volumes. These are all calibrated in SI units, the milliliter. A milliliter is the same thing as a centimeter cubed, or for those of you who have experience in the medical profession, sometimes called a cc, a cubic centimeter. So milliliter, centimeter cubed, cubic centimeter, all the same unit. So in table 1.2, there is a list of what are called the SI, the International System, base units. These are the 7 base units that are used in the sciences. All other units that we have are derived from these 7. So for example, the first one there is called length, and the unit is called the meter, and the symbol for the meter is a lowercase m, so length meter. You might say, well, wait a minute, there's more than 7 out there. What about area, or what about volume? And it turns out area and volume are derivatives. You can get area from length, and you can get volume from area or from length. You can get weight, you can get force from mass. So these are the 7 that are required so that you can get all of the other units. So I'm going to go through them. The mass is a kilogram. That's the standard unit in the SI system. And the abbreviation for kilogram is kg. If you go to a gym and you're lifting weights, there is becoming more and more common for people to quote the weights that they're lifting in kilograms as opposed to pounds. As a side note, I won't go into this in detail, pounds is actually not a unit of mass, it's a unit of force. Kilogram is a unit of mass. The unit of force in the SI system is called the Newton. Time is the same in the English system. It's the second, and the abbreviation for second is a lowercase s. Electric current is the ampere, and that's uppercase A. That's the abbreviation. Temperature is the Kelvin, although we'll see in this section that there are other units of temperature that we use. And the abbreviation for that is an uppercase K. Amount of substance is the mole. We'll use that quite a bit in Chapter 3. And the abbreviation is not much of an abbreviation. It goes from 4 letters, MOLE, to 3 letters, MOL, but that's the abbreviation. Luminous intensity, if we're talking about the intensity of light, is the candela, and the abbreviation for that is CD. So there are 7 SI base units. It makes a note here that one of them actually has a prefix in it. The kilo is the K, and those are our base units in the SI system. Now, prefixes are shown in Table 1.3. Prefixes are used to represent measurements. Remember, a measurement is a number with a unit. So these are prefixes that are used to represent large numbers and small numbers. Sometimes our base units don't quite do a good job of showing us the size of something. So let's go through them. I'm going to pronounce them for you so you know what they are. The large ones first. Tera, capital T is the abbreviation, the symbol for that, means 1 times 10 to the 12th. Now, using units that you might be familiar with, 1 times 10 to the 12th is a trillion. So the national debt is often referred to in trillions of dollars. That would be tera dollars. So the measurement would be represented by putting the prefix, so capital T, with the unit of measure, which might be a gram or a G. So here we're showing you a unit there, the gram. So 1 times 10 to the 12th, 1 followed by 12 zeros, is the teragram, TG, and that would be 1 times 10 to the 12th grams. Notice they're using something called exponential notation here, 10 to the 12th. We'll talk about that later. Giga, Giga. Giga is 1 times 10 to the 9th, 1 followed by 9 zeros. That'd be a billion in terms of terminology we're more familiar with. But if you want to be cool out there, you could say, hey, he's a giga-heir as opposed to a billionaire, right? Giga is the scientific term for a billion. A gigawatt is a GW, and that's 1 times 10 to the 9 watts. That's the unit of energy, is the watt. Actually, it's the unit of power. I'm sorry, it's the unit of power. Mega is a capital M, 1 times 10 to the 6th. An example measurement would be a megahertz. And if you've ever listened to FM radio, the frequencies of FM radio, not many people listen to radio these days, but the frequency of radio is in megahertz. So, for example, your radio station might be 97.1. That 97.1 means 97.1 megahertz. So a megahertz is 1 times 10 to the 6 hertz. Kilo, 1 times 10 to the 3, 1,000, right? So a kilometer or kilometer is a km. So you're showing their km. The kilo is the prefix, and we're using the symbol for the prefix there. And then the unit of measure is the meter. So km is 1 times 10 to the 3 meters. Now we get to some prefixes that are less than 1. These are used to represent small numbers. And some of these are more common than others, but for the most part we'll use most of these. Deci, or deci, is a lowercase d, and that's 0.1, 0.1, a tenth, if you want to use that terminology. Or, in exponential notation, 1 times 10 to the minus 1. A deciliter, therefore, remember, notice the pattern. It's the symbol for the prefix and then the symbol for the unit of measure. A deciliter is a measure of volume. A deciliter is 1 times 10 to the minus 1 liters, deciliter. Centi, c, lowercase c. And notice that the prefixes for the numbers that are less than 1 are all lowercase. 1 times 10 to the minus 2 is a hundredth, 0.01. 1 centimeter would be 1 times 10 to the minus 2 meters. Milli, lowercase m. Remember, uppercase m is mega, big. Lowercase m is milli, small. Milli would be a thousandth. So 1 times 10 to the minus 3. A millimeter, therefore, would be 1 times 10 to the minus 3 meters. Micro is the one in this list that actually uses a Greek symbol, not an English symbol. And the Greek symbol is called the mu, M-Y-O-O, if you wanted to spell it out, mu. And so micro is 1 times 10 to the minus 6, a millionth. So a microliter, which is a pretty small volume, is 1 times 10 to the minus 6 liters. Again, micro is the prefix, L is the symbol for the liter, a measure of volume in that case. Nano, lowercase n, that's a billionth, 1 times 10 to the minus 9. A nanosecond, a very short period of time, is 1 times 10 to the minus 9 seconds. And then finally we have pico, lowercase p, 1 times 10 to the minus 12th. I guess that would be a trillionth. A picogram is 1 times 10 to the minus 12 grams. Okay? There are other prefixes out there. There's one for 10 to the minus 15, 10 to the minus 18, 10 to the minus, 10 to the 15, 10 to the 18, 10 to the 21, 10 to the 24. There are also prefixes for smaller numbers, 10 to the minus 15, 10 to the minus 18, 10 to the minus 21, 10 to the minus 24. Don't have to worry about those. You should just learn the ones, learn the ones from table 1.3. If you're interested in the other ones, those are certainly fine to learn as well. You'll find them online. You may also find them on the Alex software. Now let's talk about one type of measurement. One type of measurement is mass. So it says in here, although the terms mass and weight are often used interchangeably, and you'll notice that we do that in chemistry quite a bit. We will use the term mass when we really mean weight, and we will use the term weight when we really mean mass. It shouldn't be too big of an issue. Physicists are more strict about the meaning of that, but it tells you the difference here. They don't mean the same thing. Strictly speaking, weight is the force exerted by an object or sample due to gravity. So when something is interacting with another mass through gravity, so for example, you are on the surface of the Earth, so you're interacting with the Earth, masses attract each other, and that attraction causes a force to exist. And that force, due to gravity, we call that weight. So the reason that you fall, you feel this force pulling you down, is that the Earth has so much more mass. The force that it exerts on you is strong enough that it causes you to accelerate towards the surface of the Earth, actually toward the center of the Earth, but the surface of the Earth will stop you from moving. So we call that weight, is that force that's holding you down or pulling you down. Mass is a measure of the inherent amount of a material. And so it's a little bit more abstract because it's not quite as simple to measure it. Like you can feel a force, but you don't really feel a mass. Mass is the amount of substance that you have. So for example, air has mass. Your hair has mass. Your body has mass, and the earth has mass. Okay. So that's the amount of material. So what happens then is if you are on a world that has a different mass, your mass is still going to be the same. The mass that you have is just how much matter you have in your body, and that's not going to change. So if you're on the moon, for example, your mass would be the same. However, your weight would be different because the mass of the moon is different. So if the mass of the moon is smaller, and it is, the mass of the moon is smaller than that of the Earth, the weight that you would have would be less because the force due to the mass of the moon would be smaller. So you would weigh less, but you would have the same mass. So they're not strictly the same thing, although we will use the terminology interchangeably. So let's come back to that issue of the SI base unit of mass is the kilogram. It's the one base unit that actually has a prefix in it. And there's historical reasons for that. But chemists often measure things in grams, not kilograms. So here's how we can think about this. 1 kilogram is equal to a kilo times a gram, 1,000 times grams. In exponential notation, that would be 1 times 10 to the 3 grams. So notice the G is used as a measure of mass. That's the gram, and that's something you should memorize. We use grams a lot. If you think about it this way, a pencil weighs around 5 or 6 grams. A pencil eraser, the little tip eraser, weighs about a gram. Maybe a fly weighs half a gram. They're not very heavy. Half a gram. You as a person might weigh, maybe around 60 kilograms, which would be 60,000 grams. Okay, so that's one unit that we have to be aware of, which is mass. We're going to use it quite a bit. Another unit is the unit of temperature. And we mentioned, if you come back to table of 1.3, that temperature is measured in Kelvin, but it turns out that there's other scales that are used. So one is degrees Celsius, and another one is degrees Fahrenheit. So this discusses those three temperature scales. You can interchange between Kelvin and Celsius very easily. If you know the temperature in Celsius, you just add 273.15, often just 273, and that will give you the temperature in Kelvin. So if you look at sample problem 1.1, this will show you how to do a conversion between Celsius and Kelvin. Okay? You're just going to use equation 1.1. So for example, the normal human body temperature can range over the course of a day from about 36 degrees Celsius in the early morning to about 37 degrees Celsius in the afternoon. So degrees C meaning degrees Celsius, that's temperature. Express these two temperatures and the range they span using the Kelvin scale. So notice the sample problems will give you a strategy. They'll set up the problem and then they'll show you the solution to it. So you'll have that. So I recommend you do all the sample problems that we cover in these sections. Actually, I would do every sample problem in chapter 1, 2, and 3 that there is. I would also do every practice problem A and B. The conceptualized C are up to you. You can try those if you'd like to, if you have questions about them, because their answers are not there. If you want an answer, just get in touch with me. You can call or text or email me, and we can go over it. But do the practice problems A and B as well. The answers, of course, are clickable right there. So that is one to try. There's also the Fahrenheit scale. Now, I'll be honest with you, we don't use that this much anymore in chemistry. This will show you how to go through it, though. It shows you the two equations for that conversion. If you have the temperature in Fahrenheit and you want to find the temperature in Celsius, you take the temperature in Fahrenheit and you subtract 32. Then you multiply it by 5 divided by 9. And so that'll give you the temperature in Celsius. If you have it the other way around, if you have the temperature in Celsius and you want to find it in Fahrenheit, you take 9 divided by 5 times the temperature in Celsius, and then you add 32 to that. The order is important. Multiply 9 divided by 5 times the temperature in Celsius, then add the 32. So sample problem 1.2, this will show you an example of going through those conversions as well. Again, try the practice problem A and B. C is optional. Finally, the last example in here is going to be discussing the issue of volume and density, which is an example of a derived unit. If you remember, we said there were 7 base units. Well, there are also derived units. So these are units that come from the base units. Volume is derived, density is derived, meaning you need more than one base unit. So let's look at volume first. Here's an example of volume. Volume of a cube is the length cubed. So this is a three-dimensional object, so the volume is the amount of space that that object occupies. So it's showing here a couple of volumes. It's showing you the centimeter cubed or the millimeter, actually it's showing you 3, the millimeter cubed, the centimeter cubed, and then the decimeter cubed. A decimeter cubed, meaning a decimeter times a decimeter times a decimeter, length, height, width, is equal to a liter. A liter is 1 decimeter cubed. A milliliter is equal to 1 centimeter times 1 centimeter times 1 centimeter, a centimeter cubed, or a cc, as I said earlier. A millimeter cubed, which is on the right at the bottom, tiny, tiny little thing, a little millimeter cubed, is a millimeter times a millimeter times a millimeter times a millimeter times a millimeter. Okay, it's easy to get tongue-tied on these problems. So that's figure 1.10. That's volume. There's also density. Density is a derived unit. Density is defined as the mass of an object, how much material you have, divided by its volume, V. So it's actually 2 derived units because volume is a derived unit, length times height times width, but then density is mass over volume, so it's also a derived unit. Okay? Mass is not a derived unit, it's one of those base units. So in this sample problem 1.3, you will see an example involving density. So I'd like you to try that as well. Ice cubes float in a glass of water because the solid water, the ice cube, is less dense than the liquid water. Calculate the density of ice given that at 0 degrees Celsius, a cube that is 2.0 centimeters on each side has a mass of 7.36 grams, and then determine the volume occupied by 23 grams of ice at 0 degrees C. So again, the sample problems will give you the strategy, the setup, and the solution. For this one, well, they're telling you what the length is of the cube. Remember, the volume of a cube is the length times the height times the width. So that would be 2.0 centimeters times 2.0 centimeters times 2.0 centimeters. And then it gives you the mass in grams, 7.36 grams. Density is mass over volume. Okay, I would recommend that you actually do memorize equation 1.4. That'll be useful for you. Density equals mass over volume. So try the sample problem 1.3. Try the practice problem A and B. C, conceptualize is optional. And then finally, there is a short discussion here about why units are important using an example of NASA losing a very expensive satellite that was sent all the way to Mars to learn about the Martian weather system. Many scientists and engineers were very excited about this. Unfortunately, they lost the entire satellite. It just essentially burned up in the atmosphere because of unit errors. The scientists and engineers made unit errors. So you could read through that. It's an interesting, what's called a cautionary tale. Finally, there's the checkpoints in here. The checkpoints are just extra practice, and I highly recommend extra practice. So try these checkpoints, which will go through some temperature conversions and some density conversions. That'll give you some practice there going through that. So lots of problems in this one. In this section, it's the first section where we have any problems, and so you want to do all of those problems. This is a problem-based course. Practice problems. I recommend getting a composition book or a binder and just doing the problems and keeping your work in an organized manner so you can refer to it as you prepare for exams. So this is the end of section 1.3.